The Queen opened Calder Hall nuclear power plant in Cumbria, England on 17th of October 1956. It had been connected to the national grid 2 months earlier, making it is claimed, the first reactors who supplied commercial quantities of nuclear-generated electricity. As part of the new Elizabethan age, as the time was called, it heralded a plentiful supply of cheap, safe and clean energy. It proved to be a little more complicated than that. Edward Teller, the father of the H-bomb, had said of the risks from nuclear reactors in 1953, "The hazard is crudely analogous to conducting both explosive and virulent poison production under the same roof." The thinking about accidents in these early years was based on what we might call a worst-case scenario. By the 1950s, the benchmark became the worst conceivable accident. When people made some calculations about the effects of one of these, it was realised that they were still usually far above what was likely to be acceptable. The industry called for something more realistic. Thus, in 1960 was born the Maximum Credible Accident, MCA, smuggling in some recognition of the likelihood of accidents. The two possible causes of most concern were a reactor runaway and a loss of cooling of the core. One innovation that helped make reactors safer was the introduction of secondary containment in the 1950s, a leak-tight dome built around the reactor. As time progressed, systems were added inside it to manage any radioactive material that might be released into it, with clean-up systems and water sprays. It was important to make sure that the pressure inside would not rise too high and cause a structural failure. I mention this because one MCA decided upon for a light water reactor was loss of coolant because of a breach in the cooling system, a LOCA, followed by fuel meltdown and partial release of the reactor contents to the secondary containment, the dome. It was assumed incredible that the secondary containment would fail, so the MCA would cause a very expensive mess, but no one would die. More of this later. Over the next decade or so, the MCA morphed into the design basis accident. This specified the largest accident the reactor system should be designed to cope with to ensure the public's health and safety. Avoiding a judgment on credibility, it was still pretty vague how to choose the DBA. A modern definition, a postulated accident at a nuclear facility must be designed and built to withstand, without loss to the systems, structures and components necessary to ensure public health and safety. In practice, a judgment had to be made on the basis of risk. It often meant that the reactor system had to be designed to cope with a single failure, but not with a second independent one in a protection system. I should mention a design principle called defence in depth. Originating in 1967, it recognised that there were several barriers preventing the escape of fission products from a reactor, ranging from the fuel matrix, the fuel cladding, the primary containment, right out to the secondary containment. There were also other lines of defence, soundly designed safety systems, trained staff, good maintenance, regular inspection. The principle evolved over the following decades, but remained at the heart of nuclear safety. My summary: there should be more than one barrier if anything went wrong, and the barriers should be independent. This is all rather theoretical, so we should ask, what were the main things done to engineer safety? Once a low has happened and cooling has been lost, the fuel will heat up, and if nothing is done, it will maybe melt. This will happen even though the reactor would likely shut itself down due to lack of moderating water, because of the massive amount of heat produced by the still highly radioactive fuel. The fuel cladding will fail, and a cocktail of fission products will be released and escape from the breach in the cooling circuit. Some means is necessary to cool the fuel. The idea for an emergency core cooling system, an ECCS, originated in the mid-1960s. It involved large tanks of borated water. Borated because it will reduce the reactivity of the core, which stand ready so the water can be injected into the reactor, cooling things down until other systems come online. Things didn't go too smoothly. In 1970, some half-scale experiments showed that pumping water into a reactor full of steam and very hot water might not be that easy. The AEC set up a series of hearings that lasted 18 months and generated 22,000 pages of transcripts that showed that experts differed on the likely effectiveness of an emergency core cooling system. Nuclear skeptics had a field day, and the AEC lost some of its credibility. Anyway, emergency core cooling systems became a standard feature of light water reactors. One of the earliest and abiding worries about reactors was that they would somehow run away. Reactivity would rise out of control, with disastrous consequences. Fermi in his tennis court worried about it, and had a man poised with an axe who, on the command, would slice through a rope and send a big chunk of neutron-absorbing material plunging into the pile, shutting down the reactor almost instantly. It was called a scram, perhaps reflecting the reactions of those present. Since then, the emergency shutdown system has become automatic and scrams the reactor if anything seems amiss. The nightmare was that it didn't, in what is known as an anticipated transient without scram, an ATWS. Designers went to some trouble to devise shutdown systems that were very reliable. They scrammed the reactor when needed, but not when it wasn't. In 1963, the system at the German Karl reactor failed unexpectedly under test. A detailed investigation showed that the cause was a change made to the protective coating of the electrical relays. There were several independent systems that triggered the scam system, good practice to achieve high reliability, but they all used the same type of faulty relays. This was a so-called common cause failure. The likelihood of failure to operate is, in practice, quite difficult to estimate. There was a thought at the time, and it broadly persists, that achieving better than a failure rate on demand of 0.01% of an emergency shutdown system is a big challenge, mainly because of the possibility of common cause failure. However, vendors regularly claimed reliability 10 to 100 times better than this. By 1973, it was a requirement for new reactors that they had to have two independent systems. There followed guidance on improving systems fitted to older reactors. But it was not until 1984 that the ATWS issue dropped from the nuclear headlines. Of course, there was always the real nightmare scenario for a PWR that the primary containment might fail catastrophically, exposing the core and quite probably demolishing the secondary containment. Such accidents were hardly considered in safety assessments, being deemed effectively incredible, since it was thought that the pressure vessel would leak before it failed, and the reactor would then be shut down. In other words, that regular and thorough inspection would be adequate. The incredibility of all this took a knock in the 1960s when some British research suggested that reactors might be operating in the temperature range where vessels were brittle rather than in the ductile region, which was the justification for the conviction that they would leak before breaking. A 10-year research programme at Oak Ridge was required to reassure regulators. The inspections have revealed occasional small cracks which have been repaired. In 2002 there was some surprise, therefore, when a cavity the size of an American football was found in the head of a reactor at the Davis-Best plant. It was a result of corrosion near a control rod penetration. Of course, it was found before it did any harm, but by then it had nearly eaten through the wall of the vessel. Of the 150mm thickness, there was just 10mm left, holding back a pressure of about 2,500 psi. The consequences, had it gone unnoticed, were probably not catastrophic failure of the vessel, but there would have been a serious loss of reactor coolant. As it was, the reactor was shut down for 2 years while repairs were made to the vessel. One of the driving forces behind safety thinking was the Price-Anderson Act of 1957. As a means of encouraging the development of commercial nuclear power, this limited the compensation payable by utilities in the event of an accident above a certain level, which corresponded with severe accidents. The government would cover claims. A controversial matter with non-nuclear utilities who had no such support and argued that it was unfair. From the early 1950s, people began to think seriously and in more detail about the likely consequences of severe accidents where radioactivity was released into the environment. They were later referred to as beyond design bases. The first big step forward was actually in consequence analysis with the Brookhaven report, WASH 740, published in 1957. It took a largish, for the time, reactor of 500 megawatt thermal and postulated that 50% of the fission products contained in the core were released to the atmosphere as a cloud of gas and inhalable particles. This dispersed in the atmosphere and was inhaled by and irradiated the surrounding population. A representative distribution of people for a site in the USA was assumed, causing death and injury. Different possible meteorological conditions were considered using the best atmospheric models of the time. In short, the study went about its business in a way that many later studies were to follow. The headline results were that there would be as many as 3,400 deaths, 43,000 injuries, and it put the affected area at something under 150,000 square miles at a maximum. The actual numbers would depend on the meteorological conditions, and these worst case figures were possible only in about 10% of accidents. The report then set about the task of putting things in proportion by showing that such an accident was highly unlikely. All the experts agreed that this was so, but several balked at actually putting numbers to it. The rest of them agreed that it was somewhere between once per billion years and once per 100,000 years. So a risk of between 10 to the minus 9 and 10 to the minus 5 per year per reactor. To put the lower number in perspective, it is about 1 billion years since the first plants appeared on Earth. Sex started a couple of 100 million years before that. When the report was revisited in 1964, prompted partly by an upcoming review of the Price-Anderson Act, there had been advances in estimation of the consequences. However, these rather inconveniently suggested that Brookhaven had massively underestimated the casualties. So it became important to refine the likelihood estimates. Sadly, the first bunch of expert advisors concluded that, on the basis of actual experience, they were reasonably confident that it was less than once per 500 years. Not terribly comforting. Some other experts stood by the methods and conclusions of Brookhaven. After some argument with the AEC, the report was hushed up. All that was said about the review was that it had reached conclusions very similar to those of WASH 740. The Task Force on Nuclear Safety, Licensing and Risk, set up by the AEC under Malcolm Ernst, reported in 1973. It concluded that the complexity of reactors made quantitative risk assessment impossible for them. Given the obvious need to put the casualty calculations in perspective, this was grim news. Fortunately for the AEC, not everyone agreed with it. In response to reliability problems with complex military systems, such as missiles, in the late 1940s and 50s, several techniques were developed which could link the probability of failure of individual components with failure of the whole system. One of these, fault tree analysis, was taken up by nuclear safety analysts. Another complementary technique, event tree analysis, was taken from business decision theory. It was these two methods taken together that made it possible to give the first grounded estimates of the likelihood of a reactor accident. It took until 1975 to do it. Just a couple of years after the Ernst report said it could not be done. It was not that engineering reliability principles had not been developing in the nuclear business in the 1950s and 60s. The search for a more rational and balanced approach to the whole problem seems to have started with Ernie Siddall, an engineer at AECL's Chalk River establishment, in 1956. Siddall set down some of the essential principles of the use of redundancy and coincidence in reactor safety systems to improve their reliability. 1973 saw the publication on a fairly limited distribution of the 500-plus page report WASH 1250. This dealt with many aspects of the safety of nuclear power, from the effects of routine emissions and the problem of nuclear waste to accidents, including severe ones. On the accident issue, it could report and expand on the various analyses that had taken place and describe the experiments and initiatives that had been taken on consequence mitigation. However, it had little or nothing to say about the likelihood of any serious accidents, largely because nothing of significance had been done on the subject. However, just before the appearance of this report, another project, the Reactor Safety Study, led by Professor Norman Rasmussen, began. Prompted by the questions about the reliability of emergency core cooling systems, the failure of WASH 1250 to say anything significant about accident probabilities, and likely wrangling over the upcoming extension of Price-Anderson, the study started in 1972. Some 40 engineers and scientists worked to produce WASH 1400, the Rasmussen report, in 1975. It was by far the most detailed study of consequences and probabilities of severe accidents so far. The study moved forward the analysis of consequence with detailed modelling of the so-called source term, the quantity and mix of the radioactivity released to the atmosphere, the degree of dispersion in the atmosphere, the consequential doses received by members of the public, and the casualties that arose. It allowed for the different atmospheric conditions and considered a number of possible reactor locations and population distributions. However, all this was much more of the same. What was really new was the analysis of the probabilities. Peach Bottom Unit 2, a BWR, and Surrey Unit 1, a PWR, were chosen as reference cases, and fault trees were initially developed for most of the major safety-related features, but it was soon realised that a comprehensive analysis based on creating and integrating the fault trees for a complete reactor system was simply not feasible. The system was so complicated, and time and resources were anyway limited. There was a shortcut, a shorter one, if event trees, which could be developed reasonably quickly, were used to model the development of accident sequences. The time-consuming fault trees were then needed only for the protection subsystems that were involved in the accident sequence that actually led to exposures of members of the public. The number of individual accident sequences generated was about 1,000, and these were then allocated to one of 15 release categories, 10 for PWRs and 5 for BWRs. These were chosen to be representative of releases to the atmosphere in terms of isotopic composition, elevation, energy and time profile. From a study of the event trees of the dominant accident sequences in each category, the probability per reactor year of a release in each release category was estimated. The approach drastically reduced the scale of the subsequent calculation, in fact making them tractable. The report aimed to estimate two types of risk: individual risks to people living quite close to reactors, and societal risk arising from a programme of 100 light water reactors. The headline value on individual risk was that early fatality risks to individuals living within 25 miles of a reactor, some 15 million people, was 2 times 10 to the minus 10 per person year. The societal risk was expressed using FN curves, which showed, for example, the early fatalities from accidents at the two types of reactor, versus the frequency per year of this number being exceeded. This example, when we adjust the programme for 100 reactors, shows that 100 or more early fatalities were predicted to occur on average every 100,000 years. More than 3,000 early deaths were expected every 10 million years. The other graphs show the likelihood of increases in annual cancer rates and annual incidence of genetic defects. You should note that the total number of cancers associated with accidents is about 30 times this annual rate. A similar adjustment is needed to the genetic numbers. And you'll see I've also included a graph that shows the predicted areas of contamination. The Lewis Committee, set up to review the report, praised it for revealing the potential of fault-tree analysis and for a methodology that could lead to a more rational regulation. However, they criticised several aspects of the work, including the presumption that external events and human factors made a negligible contribution to the overall risk, an understatement of the uncertainties inherent in many of the calculations, and the over-optimistic executive summary, as much as most people read, which failed to give an adequate description of the uncertainties in both accident consequences and probabilities. They called it advocacy rather than a summary. Hal Lewis, the committee chair, commented that the unacknowledged uncertainties were so large that I can't say anything that would be useful. I can't learn anything from WASH 1400 that would help me on it. Many similar probabilistic safety assessments were conducted around the world, but they never seemed to achieve the promise they offered, at least to some, in the 70s. One area that was never really incorporated was the human element. It just proved very difficult to quantify. And external events such as earthquakes just contributed to the main problem, the uncertainties. Mike Haynes, who'd been heavily involved in the Sizewell analysis, could say at the turn of the century, risk analysts are only at the threshold of performing comprehensive uncertainty analyses. Rather than being the hoped-for panacea, probabilistic safety assessment became just another factor in making decisions about nuclear safety. The progress was, as the US Nuclear Regulatory Commission said, that decisions were now risk-informed.